Hi everyone, let's go over section 3.3, complex numbers. Our objectives are to be able to perform arithmetic operations on complex numbers and solve quadratic equations having complex solutions. We begin with the definition of a number that we call I. Complex numbers have applications in the physical sciences, such as in electrical engineering. You may have heard them referred to as imaginary numbers. And even mathematicians believe that this is a little bit of an unfortunate name. The name imaginary numbers tends to make you think that there is no practical purpose for these numbers, but in fact, there certainly is. For much of our purposes, the introduction of I and imaginary numbers is just going to allow us to continue mathematics when we approach the square root of a negative number. We know that in the real number system, you can't take the square root of a negative number. For example, you can't take the square root of negative 25 because 5 times 5 is positive 25, and even negative 5 times negative 5 is positive 25, since a negative times a negative is a positive. So there is no number times itself that equals the square root of a negative 25. And so we introduce I. I is defined as the square root of negative 1. And so what this does is it allows us, if we have the square root of something like the square root of negative 25, we can rewrite negative 25 as negative 1 times positive 25. If you have the product of two numbers under a radical sign, you can separate them, the square root of negative 1 and the square root of positive 25. The square root of negative 1 is this number that we just introduced called I. The square root of 25 is, of course, 5. And so the square root of negative 25 is 5i. Now, I can be very useful, but something that is just as useful is I squared. Now, let's say we have I squared. We know that I is the square root of negative 1. So if we square that, we know that a square undoes a square root, and we're just left with negative 1. So I squared is just negative 1. And that fact can be just as useful. Let's look at how we would use this in new information to solve a quadratic equation. Now, this quadratic equation does not have a linear term. It has an x squared term. It does not have an x term, which is our linear term, but it does have a constant plus 1. So we know to solve something like this, we could subtract 1 from each side of our equation. And of course, 1 minus 1 is 0. So I'm going to bring down the x squared. And 0 minus 1 is negative 1. Next, I would take the square root of each side of my equation, because the square root of x squared is x. Now, when I'm solving a quadratic equation and I take the square root, I want to put a plus or minus here. And the square root of negative 1 is this new number called I. We know in a quadratic equation that we often get two answers, and so this plus or minus is going to be something that shows up a lot when we're solving quadratic equations. Now, I is not a real number, but it is an imaginary number, and by introducing I, it allows the math to continue. Now, in that example, we kind of stopped with x equals plus or minus I, but often we can keep going, working our math, and sometimes even by introducing imaginary numbers, if we keep working, they might actually just go away and just allow us to resume in the real number system. We'll see examples like that at some point. So when you have an expression where you're taking the square root of a number, a negative number, like the square root of negative 25, and if a is positive, then of course negative a is negative. And so you simply introduce I, and that sort of takes care of the square root of the negative part. Now, when you take the square root of negative 1 and it becomes I is not under the radical sign. So let's use this knowledge to simplify these expressions. So the square root of negative 12, once again, like we did with negative 25, I consider a negative 12 as negative 1 times 12. And so I can separate the square root of negative 1 and the square root of 12. Now when I simplify the square root of 12, I'm going to rewrite 12 as 4 times 3 because I can simplify this a little bit. Of course, the square root of negative 1 is I, and I can think about the square root of 4 and the square root of 3 separately. So I'll come up here to finish this problem. I have I. Of course, the square root of 4 is 2, and then I have the square root of 3. So remember, anytime you have a number under the radical and a square number divides evenly into that number, you will want to simplify the radical. So the square numbers, of course, 1 is the square of 1, but that's not very helpful. 4 is the square of 2. 9 is the square of 3. 16 is the square of 4. 25 is the square of 5. 36 is the square of 6. 49 is the square of 7. 64 is the square of 8. 81 is the square of 9, and 100 is the square of 10. And of course, I could keep going. So when we're simplifying radicals, we are going to look at our number, such as our number 12, and see if any of these square numbers divide evenly into it. And that's why I rewrote 12 as 4 times 3. Now, if I'm leaving my final answer, I will probably put the 2 and then the I and then the square root of 3. And so the square root of negative 12 can be rewritten as 2i square roots of 3. Now for example number 2, I can think about this as the square root of negative 1 times 2. I can separate the square root of negative 1 and the square root of 2. Now earlier I could simplify the square root of 12, but I'm not going to be able to simplify the square root of 2 because none of these square numbers divide evenly into 2. It's too small. So the square root of negative 1 is I. I can't simplify the square root of 2 any further. So when I write it, I'll just keep the I in front, the square root of 2, and I'll write my final answer like this. Moving on to number 3, I have 4 plus or minus the square root of negative 8 divided by 2. So I'm going to focus on that square root of negative 8. Because I have the square root of a negative, I'm going to rewrite it as negative 1 times 8. Everything else I'm keeping the same. So I know I can separate the square root of negative 1 and the square root of 8. But I'm going to write 8 as 4 times 2 because the square root of 4 is a square number, and I can take the square root of 4. So I have 4 plus or minus, the square root of negative 1 is I. I can separate the square root of 4 and the square root of 2. Then of course I can take the square root of 4, since the square root of 4 is 2, but the other 2 under the radical is just going to stay. Now I can separate this into, let me move this up a little bit. I can separate this into 4 over 2 plus or minus I times 2 square roots of 2 over 2. Of course, this first part, 4 divided by 2 is just 2, plus or minus. Those two factors of 2 cancel, and I can just call it I square roots of 2. So I can simplify that a little bit. So notice that I'm not going to keep a negative sign under a radical. I'm going to introduce I and then simplify as much as I can. Now, when I'm taking the square root of two things that are negative, so I can think about this as the square root of negative 1 times 13 times the square root of negative 1 times 13. I can separate these, the square root of negative 1, the square root of 13, the square root of negative 1, and the square root of 13. I can rearrange this. Well, I can call the square root of negative 1 I, of course. And then I have the square root of 13, and another I, and the square root of 13. I can multiply these together and get the square root of 169. I can multiply the i's together and get I squared. Now remember earlier we said that I squared is equivalent to negative 1, and of course the square root of 169 is just 13. And negative 1 times 13 is negative 13. Now I broke that apart into as many minuscule steps as I possibly could, but you might just be able to tell that that's what that would have equaled. I could have actually done this a little bit simpler, but I just wanted to walk through that exercise with you. I know that when you have the square root of a number and the square root of a number, it would be the square root of negative 13 squared. The squaring and the square root undo each other, and you would simply be left with negative 13. So you could have gotten there much simpler, just depending on how your brain thought about this particular problem. Now for number 5, I'm going to rewrite this as, again, if you want to just do a little shortcut, I know that's just going to be I times the square root of positive 2 and I times the square root of positive 32. I can put the i's together. I times I is I squared, and 2 times 32 is 64. The square root of 64 is 8. I squared is negative 1, and negative 1 times 8 is negative 8. So again, if you're solving problems like this, for example, when you're doing problem number 2, you might just know that, okay, that's just going to be I times the square root of 2. You don't necessarily need to show all of those steps, but I did want to at least walk you through the process of why these will turn out the way that they do. So this form, a plus bi, is the way we write what is called a complex number. Okay? And a complex number is going to include all of the real numbers that we know, as well as those with imaginary components. So the A part is going to be called the real part, and B, the number before I, is called the imaginary part. So let's look at the examples given and let's try to break those apart. The first complex number we have is 2 minus 3i. If I write it in the form a plus bi, it's going to be 2 plus negative 3i. So the real part is 2, that's a, and the imaginary part is negative 3, that's the coefficient of I. The next one is already in the form a plus bi, it's 8 plus 6i, where the real coefficient is 8 and the imaginary coefficient is 6, since 6 is the coefficient of I. Negative 7 is a perfectly real number. It does not have an imaginary component. But if I wanted to write it in complex number form, I would say negative 7 plus 0i, where the real part is negative 7 and the imaginary part is 0. In our last example, we have an imaginary component, but no real component. So I would write this as 0 plus 2i. This time the real part is 0 and the imaginary coefficient is 2. Now that we know a little bit about complex numbers, let's look at how we would do math with complex numbers. It's actually pretty straightforward. It's just like combining like terms when you add or subtract complex numbers. I is not a variable because its value does not vary. I is always the same thing. I is always the square root of negative 1. However, when we're doing algebra, I will behave like a variable. So if I'm adding these two complex numbers, I'm just going to add the real parts, negative 2 and 6, and I'm going to add the imaginary parts, positive I and negative 2i. So negative 2 plus 6 is 4, and then I have 1i minus 2i, which is negative 1i. Always put the real component before the imaginary component to have your number in standard complex number form. In the next example, I have negative 3i, which has no real component. So it's like having 0 minus 3i. And then when I look at this second complex number that I'm subtracting, remember to subtract 4, but also to subtract negative 5i. So I'm subtracting 4, I'm subtracting a negative 5i, which means I'll be adding 5i. So I've got my real component 0 and my real component negative 4. I'll combine those. Then I have my imaginary components. Minus 3i and plus 5i makes plus 2i. So just be sure if you're subtracting that you subtract the real part and you subtract the imaginary part. So you have to distribute the minus sign. And minusing a negative is the same as adding a positive. So even though I is not a variable, it behaves as if it is one when you're doing certain things in algebra. If we multiply complex numbers, it's just like multiplying two binomials with variables. Just don't forget this little tidbit of information. I squared is negative 1, and also we want to leave our answer in standard form, a plus bi. So when I have two binomials such as these representing complex numbers, I'm going to make sure that each one of these numbers multiplies with each one of these numbers. So I'm going to do negative 3 times 1 and negative 3 times minus I. Negative 3 times 1 is negative 3, And negative 3 times minus I is plus 3I, because a negative times a negative is a positive. Now I'm going to do 2I times 1 and 2I times negative I. 2I times 1 is positive 2I, and 2I times negative I is negative 2I squared. So I can simplify this. I have my minus 3. I can combine 3I and 2I to make 5I. And also, don't forget that I squared is equivalent to negative 1. This is how multiplying complex numbers differs from multiplying two binomials. Usually the letter is just a variable, but in this case, I is not a variable because I squared is negative 1. So of course I can simplify this a bit further. Negative 2 times negative 1 is positive 2. And now I can combine my two constants. Negative 3 plus 2 is negative 1. And then I have my plus 5i. So I have my complex number in standard form, a plus bi. I used to always forget to simplify it by inserting negative 1 in the place of I squared. Now, when you are dividing complex numbers, what you're going to do is simply multiply the denominator and numerator by the complex conjugate. If you have a complex number a plus bi, the complex conjugate is a minus bi. So complex conjugates are two complex numbers that are exactly the same except for the sign in the middle. Now, by multiplying by a complex conjugate, we're going to create a nice rational denominator. And for some reason, mathematicians love nice rational denominators. Let me demonstrate with these examples here. So I have 3 divided by 2 minus I. My denominator is a complex number, 2 minus I. So what I'm going to do is I'm going to multiply numerator and denominator by the complex conjugate of 2 minus I, which is 2 plus I. Complex conjugates are two complex numbers that are the same except for the sign in the middle. By doing this, this is going to give me a nice rational denominator. In the numerator, I'm going to just distribute 3 times 2 and 3 times I, and this is going to become 6 plus 3i. In the denominator, I'm going to multiply each of those two numbers times each of these. So I'm going to do 2 times 2, which is 4, 2 times I, which is 2i, and then I'm going to do minus I times 2, which is minus 2i, and minus I times positive I, which is minus I squared. Believe it or not, this denominator is going to simplify nicely. I'm going to just keep my numerator the same. First of all, notice that you have a plus 2i and a minus 2i. Those cancel each other out because they add to 0. So I have 4 minus I squared. But remember, I squared is negative 1. So I have 6 plus 3i. I have 4 minus a negative 1, which is the same as 4 plus 1, or 5. Complex numbers are written in the form a plus bi. So I need to take each of these, 6 and 3i, and divide them by 5. So I have 6 divided by 5 as my real component, and 3 divided by 5 as my imaginary component. Notice my denominators are just a nice rational number, 5. And this is considered better than what we started with. In the next example, my denominator is simply I. And so how can I make I a nice rational number? Well, I don't exactly need a complex conjugate here. What if I just multiply the numerator and denominator by I? Well, then my denominator is just going to be I squared, which is, of course, just -1. But when you have a fraction and you multiply the denominator by something, you must always multiply the numerator by the same thing so that you're not changing the value of the number. So I have 4 minus 2i times I. So the I is going to distribute times the 4. 4 times I is 4i. And minus 2i times I is minus 2i squared. Now remember that I squared is -1. So basically I have 4i plus 2 over -1, because -2 times -1 is +2. Now when I separate these, I'm going to divide each of these by -1, so that will become minus 4i and minus 2. But I always want to put the real part first and the imaginary part second. So this one simplifies nicely so that it's not even a fraction anymore. In this next one, before I multiply by a complex conjugate, I'm going to need to take care of this squaring of the denominator. So this is going to require a little extra work here because I do need to go ahead and square 2 minus I. When you square something, it means to multiply it by itself. It's not as simple as just squaring 2 and squaring minus I. Because it's a binomial, I am going to need to multiply 2 and minus I times 2 and minus I. Now in my numerator, I have the number 3. That's just going to hang out there. I'm going to do 2 times 2, which is 4. 2 times minus I, which is minus 2i. Minus I times 2, which is minus 2i. And minus I times minus I, which is positive I squared. Now notice I have not multiplied by a conjugate yet. I am just trying to simplify this a bit. And then I'm sure I'm going to be multiplying by a conjugate very soon. So I have a 4. This time my minus 2i and my minus 2i are going to combine to be minus 4i. And then of course I have plus I squared, which is -1. So I can add 4 and -1 together in my denominator. 4 minus 1 is 3. And I still have my minus 4i. So all I've really done is taken care of squaring 2 minus I. I haven't rationalized my denominator yet. That step comes next. I see that I have 3 minus 4i in the denominator, so I'm going to multiply the numerator and denominator by the complex conjugate of 3 minus 4i. And the complex conjugate of 3 minus 4i is 3 plus 4i. And whatever I multiply the denominator by, I need to multiply the numerator by the same thing so that I don't change the value of my expression. So in the numerator, I distribute 3 times 3, which is 9, and 3 times minus 4i, which is plus 12i. And because I'm multiplying complex conjugates in the denominator, I know this is going to turn out nice in the end. So I'm going to do 3 times 3, which is 9, and 3 times 4i, which is 12i, and then minus 4i times 3, which is minus 12i, and minus 4i times positive 4i is minus 16i squared. So I have 9 plus 12i in my numerator. In my denominator, I can do some simplifying. I have my 9 plus 12i and minus 12i add to 0, and I have minus 16i squared. But I squared is negative 1. So that's going to turn into a plus 16. So I have 9 plus 12i over 9 plus 16. Well, 9 plus 16 is 25. So I can now split this into 9 over 25, which is the real component, plus 12 over 25i, which is the imaginary component. All right, next we're going to simplify powers of I. And I kind of enjoy this. It's kind of like a little puzzle. To simplify powers of I, use the fact that I squared is negative 1. Here's an example. We can simplify I to the power of 17 if we rewrite this as I times I to the 16th power. What you don't see there is an invisible 1, which is your exponent on I. Now we can take our even power of I, 16, and we can rewrite that as I squared I squared to the power of 8. 2 times 8 is 16. That's why we can do this. Now again, since I squared is negative 1, we can substitute that. And negative 1 to the power of 8 is positive 1. Anytime you take a negative number to an even power, it's going to be positive. Let me demonstrate. If I have negative 1 to the power of 8, it means I have 8 negative 1s multiplied together. And when you have an even number of negatives, they can pair up and cancel each other out and make a positive. Because a negative 1 times a negative 1 is a positive 1. And so I have 4 positive 1s, which gives me my answer of positive 1. And of course, positive 1 times I is I. So I to the 17th can be simplified to simply being I. Let's practice with I to the 21st power and I to the 103rd power. So I to the 21 can be rewritten as I times I to the 20th, because this is I to the power of 1 times I to the power of 20, since 20 plus 1 is 21. Now the reason I do that is because, excuse my dog, I can write this as I to the power of 10, I squared to the power of 10, which is what I want to say. So I have I know that I squared is negative 1. Once again, I'm taking negative 1 to an even power, negative 1 to the 10th power. So earlier I did negative 1 to the 8th power. If I did to the 10th power, I would just add 2 more negative 1s, which would again cancel each other out and make a positive 1. And I would still get positive 1. So I times 1 is I. So I to the 21st power is also I. That may cause you to think, is every power of I? No, it isn't. And I think we'll see that here when we do I to the 103rd power. So I can write it as I to the first power times I to the 102 power, since 1 plus 102 is equal to 103. So I'll keep I to the first power, but I'll write I to the 102 power as I squared to the 51st power, since 2 times 51 is 102. So I have I squared as negative 1, but this time I'm taking negative 1 to an odd power. When you have an odd number of negative signs, they don't all cancel out. And so you'll have an additional negative 1 hanging out there that doesn't cancel. So negative 1 to the 51st power is negative 1. And I times negative 1 is negative I. It turns out when you're finding powers of I, you'll either get a positive I, you'll get a negative I, a positive 1, or a negative 1. Every power of I is one of these. So we've introduced this number called I, which is the square root of negative 1. We've talked about how to do math with complex numbers. And now we're going to go back to solving quadratic equations that have complex solutions. We talked about this in an earlier lesson, how some quadratic equations have complex solutions. And we talked about the nature of the solutions and how this is related to the x-intercepts. So let's recall that here. We know that if you have two real solutions, that you're going to have two x-intercepts. And an example of that would be, I'm going to call this A, that you would graph the parabola and it would cross the x-axis twice, once, twice. And those would be your two real solutions. A second option is you might only have one real solution. In this case, you'll only have one x-intercept. So let me sketch for you and remind you what that looks like. This would be a parabola that just touches the x-axis in one point. In other words, the vertex is on the x-axis. Now, excuse my parabolas, they're not very pretty. They're supposed to be U's. Remember, a parabola is a U shape. It can open up or down. If you have the third option, where you have two complex solutions, this means it will not have any x-intercepts. So an example would be one that looks something like this, where the parabola does not cross the x-axis at all. We learned about several ways we could solve a quadratic equation. You might remember we could factor, we could graph and see where it crosses the x-axis, or we could use the quadratic formula. We learned how to complete the square, but that's kind of the long, drawn-out way to solve it, and so we generally will probably not be completing the square. But we want to focus on what it looks like when we have two complex solutions. So we'll end with a couple of examples of complex solution quadratic equations. Now, the beautiful thing about this example is it's already in standard form. Descending powers of x. We have x to the second power, x to the first power, a constant, and it also says equals 0. So this is beautiful. If I could factor it, I would. It turns out that this is not factorable, so I'm going to rely on the quadratic formula. Now for the quadratic formula, you want it to be in standard form. And then you're going to pick out a, b, and c. Remember, a is the coefficient of x squared, b is the coefficient of x, which in this case is an invisible 1, and c is your constant, which is coincidentally also 1. The quadratic formula says x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. So now we just substitute the numbers in. So I have negative 1 plus or minus the square root of 1 squared minus 4 times 2 times 1 all over 2 times 2. You might remember that the part under the radical sign is what we call the discriminant. It tells us a lot about the type of solutions that we have. So 1 squared minus 4 times 2 times 1 turns out to be negative 7. When your discriminant is negative, and 2 times 2 is 4. When your discriminant is negative, this means that you're going to have two complex solutions. We're taking the square root of a negative number, so we know I is going to be introduced. So I'll come up here and finish this problem. I'm going to call the square root of negative 7 I square roots of 7. And I would want to simplify this radical if possible. If there is a square number that divides evenly into 7, then I can simplify this radical. But that's not the case. In fact, 7 is a prime number, so I know that radical cannot be simplified. So I'm just going to separate negative 1 over 4 plus or minus the square root of 7 over 4, and I'm just going to put I out to the side. Now we might leave this in this form, but I do want to remind you that this answer does represent two solutions. They're both imaginary solutions, but one solution is negative 1/4 plus the square root of 7 over 4i, and the other solution is negative 1/4 minus the square root of 7 over 4i. So those are both complex imaginary solutions. If you were to graph 2x squared plus x plus 1, you would see that it does not cross the x-axis because it has two complex solutions. In fact, I could go here and demonstrate that. I can't seem to get this out of the way. So I could say y equals 2x squared plus x plus 1. And you can see that this parabola does not cross the x-axis. And that will happen anytime you have two complex solutions. Let's do our final example together. This one is also already in standard form for us, and it's equal to 0. And I know it's not factorable because I already know it's going to have complex solutions. So I'm going to jump right into the quadratic formula once again. I will identify a, b, and c. So a is the coefficient of x squared, which is negative 2. B is the coefficient of x, which is 2. C is my constant, which in this case is negative 3. So I have my formula written above, so I'm not going to rewrite the formula. I'm just going to plug everything in. So the formula says x equals negative b, so it's going to be negative 2 plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So let's see. I've got my minus 2, plus or minus, and I like to do that discriminant. And according to my earlier calculation, I got negative 20 over 2 times negative 2 is negative 4. My discriminant is negative 20, and anytime that's a negative number, I know I'm going to have two imaginary solutions. This parabola will not cross the x-axis. But I do want to do some simplifying of this because negative 20 can be simplified. First of all, I can bring out the square root of negative 1 with the I and make it positive 20. I also note that there is a perfect square number that divides into 20, namely 4. So I can rewrite 20 as 4 times 5. Now let me come up here and simplify this further. So I have negative 2 plus or minus I. Now the square root of 4 is 2, so that gets to come out of the radical, and the 5 has to stay. Square root of 4 is 2. So let's see. If I separate this, I've got negative 2 over negative 4 plus or minus 2i square roots of 5 over negative 4. Negative 2 over negative 4 is positive 1/2. And I can really take this negative away because I'm doing plus or minus here. So that doesn't really matter. 2 goes into 2 once. 2 goes into 4 2 times. So this simplifies into the square root of 5 over 2. And then I'll put I here. So I have it broken apart into its components, the real and the imaginary. And I think that is it for our notes on complex numbers. Please reach out if you have any questions about this.